wasn't aware of a microphone today, and I apologize for that, but they want to record this, so we can probably turn that volume if you like. My name is Keith Packard. I work at Intel, Open Source Technology Center, and right now we're working on a fairly long-term project to try to integrate more technology, more modern technology into the Linux desktop. And one of the big projects we're working on now is Wayland, which is a replacement Windows system for the desktop. When we talk about replacement Windows systems, everybody, or at least probably many of you, know the history of attempting to replace the Windows system in Linux desktop. We've had many failed examples. We're hoping this one will be a little more successful. One of the goals, of course, is not to make everybody rewrite all their applications all at once, but to give us a slow migration path. And so today I'm going to be talking about that migration path where we're going to be providing X compatibility going forward in the Wayland environment without any functionality or performance degradation, which seems kind of critical for most applications. So first off, I wanted to just remind everybody of what the X architecture looks like, where you have an application. The application talks to its direct rendering libraries, whether they're media libraries or OpenGL libraries. And the application talks to the X servers. The application is doing its rendering directly to the kernel, typically these days, and then it talks to the X server to get input events from the device, input devices, mouse, keyboard, touchpads, and it talks to the X server to get to negotiate for space on the screen, so it allocates geometry on the screen and gets its images presented that way. So the X server in this particular case is a classic, a very typical modern Windows system. It isn't doing anything other than simple multiplexing of output onto the same monitor and demultiplexing of input from the devices to the individual applications. A pretty simple process. In a modern X Windows system, we have an additional process in the loop called the compositing window manager. The compositing window manager is actually responsible for taking all of the application images that are provided to it. So the application constructs the image it wants to put on the screen, hands that to the X server hands it to the compositing window manager, which then does a bunch of geo-magic to glue all those images together and make little drop shadows and little animated foo-frames when you're iconifying things or switching applications, and actually put together a coherent user experience. So we have the typical modern X desktop has this separate application that's deeply involved in the presentation of the user interface. But no longer is the application talking solely to the X server, it talks to this additional process. So every keystroke you type, every gunshot you make through the 3D application in window mode goes through the application into the kernel, turned into images in the kernel, and then those images are sucked back up into the compositing manager and blown back into the hardware by the final presentation. So you have a bunch of additional processes involved. So one of the goals of the Wayland architecture is to kind of get rid of that separate process, that compositing manager. So in the Wayland environment, we take that compositing window manager and merge it into the Windows server itself. So we have a Windows system server that's an integrated Windows system server and compositing manager and window manager. That's called West End, the Wayland server. And so in this architecture, you can see the similarities. That from the application's perspective, it's still just talking to the Windows server for its geometry negotiation and input events. But then it talks to the hardware acceleration through exactly the same APIs to get stuff into memory buffers ready for presentation. So to a great extent, from the application's perspective, there's no change except for this small change in protocol here from Wayland, from the X protocol to the Wayland protocol. For the most part, the Wayland protocol is a vast simplification of the X protocol. Obviously, it doesn't have a lot of the stuff that X has. In particular, it doesn't support all of this external compositing manager mechanism, and it doesn't support all the external window management mechanism. So there's a lot of simplification we can do by tying those three technologies into a single process. So we save a bunch of time, we save a bunch of context switches, we save a bunch of memory, and we save a bunch of system complexity. It seems like an overall a pretty good idea. So what happens if you want to run an X application in the Wayland environment? Well, to run an X application, you are clearly going to have something called an X server, because X applications speak a network protocol called X. There's no way you're going to have them stop speaking the X protocol and suddenly switch to some new protocol. So there's a bunch of different options we could do. We could have the Wayland server become an integrated X/Wayland server. One of the promises of Wayland being a lightweight Windows system, the current Weston server is about 10,000 lines of code. If you merge that in with an X server and add another 500,000 lines of code or so, all of a sudden your lightweight Windows system is not so lightweight. So one of the great promises of the Wayland system with the Weston compositor is that you have a lightweight system. Well, when you glue in X, that's kind of a law. So the goal is to have the X server be a standalone process. Well, what does that do to the system? Well, that means that now you have the application talking to the X server, trying to negotiate for geometry on the screen and for input events. And then that X server has to talk to Weston. Well, how does it talk to Weston? Well, it goes through a new backend of the X server called the X-Wayland backend, which basically looks like a hardware backend to the X server from the X server's perspective. But instead of talking to hardware, it just talks to another Windows system. In this case, it talks to Weston. This looks really, really similar to a bunch of other architectures we already support. We support X on Windows, we support X on Mac OS, we support X on BNC, all these virtual Windows system on Windows system implementations that X has lived with forever. Those pretty much universally suck for performance because you're talking about emulating all the X graphics on top of some underlying native Windows system. In the X in this environment, that's not true. I'm going to show you why. So we have the XF86 backend talking to the Weston compositor, and then that, of course, talks to the kernel in some minor ways for getting information about the window buffers the application is talking about, so we can hand those off to Weston. So I'm just going to put together a picture here, but I don't have a picture. I'll describe it a little bit. So the application paints to the kernel with OpenGL or VAPI, and that constructs data in an off-screen image buffer in the kernel. That buffer is nominally owned by the X server because the X server allocates all the buffers, all the DRM buffers for the application. So then the X server passes that DRM buffer through the Wayland protocol to the Wayland server through this X-Wayland backend. And so now the data is transferred from the application to the OpenGL library, which constructs an image in memory in the kernel. And then the handle for that object is passed through the protocols to the Weston compositor. So the actual pixel data never goes through this wire. The only thing going through the wire is a name for the data. And then the Weston compositor says, oh, that handle, yeah, I know about that one. And it can hand that handle to the kernel again, and their kernel can then composite that onto the screen. So in this environment, you see this huge chain of data going from the application to the X server, to the Wayland backend, to the Weston server, all the way through OpenGL back to the kernel. That's just numbers. That's just tiny little names. There's no actual data, no bulk data transfer going through that thing, which is in stark contrast to the old X server model where all of your 2D rendering commands would go through the wire. So there's not a lot of bandwidth consumed there. There's just a couple of extra. There's an extra data, an extra context switch. But if you note here, this particular picture, here you have an X server talking, instead of talking to its external compositing / window manager, it's not doing that anymore, but instead it's talking to the Weston window system. So we aren't adding any additional latency or lag in the system at all. In fact, we're reducing it slightly. I'll explain why in a while. So the application talks to the X server, which talks to the Weston compositing window system, instead of talking to the Metacity or Mutter or whatever fancy compositing window manager you have. So instead of talking to the external window manager, I'm talking to an external Windows system. So I'm not increasing the number of processes at all. So your X application performance doesn't change at all. So what are the basic differences between X and Wayland? Where's the impedance mismatch going to occur here? Well, in the X environment, we have an external compositing manager, and in Wayland, we just slam that into the Windows system. Obviously, in the X environment, we did the external compositing manager largely because we wanted people to be able to experiment with compositing managers. We wanted to push as much of the functionality out of the X server as possible. And because the X server runs as root, you don't want to put a bunch of complicated UI frou-for-all into X server. Especially, you don't want to be trying to run OpenGL commands inside your X server that's doing a lot of complicated rendering and opening files and doing all kinds of fun UI stuff. So you want to push that outside the X server. So we pushed the whole thing outside the X server into the compositing manager. That's been actually a surprisingly successful hack. But obviously there's this additional cost, and so X always has this additional process context switch overheads for every frame on the screen. Every application update sends damage events off to the compositing manager. The best part, of course, is that the compositing manager and the X server now both have duplicate information about all the windows on the screen. So all of the information about where the windows are on the screen, who overlaps who, this is replicated between the X server and the compositing manager, which is awesome because the X server sends the compositing manager updates about the window stacking order and whether windows move on the screen. And those are asynchronous to the actual activities in the server, and they kind of have partial information. You don't really get a complete view of the system at any time. You're getting this little incremental, oh, this window moved above this other window. And so your compositing manager has to carefully track this stream of X events and try to mirror the X server's data structure internally. Most of them get it wrong. It's kind of surprising. You raise windows and you get black holes in the screen. So replicating the data structures over a network with incremental updates is hard. Moving the compositor inside the window system eliminates that because now you just have one data structure. It's a lot simpler. In X we have external window management, and in Wayland we have internal window management. The window management system is half inside applications and half inside the window system. I've got a nice slide about that later. External window management, by external I mean there's a separate application that does window management. And why did we do that in X? We did that in X because in 1987, when this was designed, systems didn't have something fancy and modern called a shared library. Yeah, there were no shared libraries when the system was designed. So in order to share common UI elements, in order to share common appearance in the screen, the only way to do that was to centralize it in a single application. The only practical way to do it. So in the X environment, we centralized it in this external window manager. As a side effect, and as a nice bonus that most of us have really learned over the years, our applications are now manageable even if the application is not responding. So if you have a wedged application, if you have a long-running application that's busy doing something, you accidentally suspend your application on the top of the screen, you can still manage it with the window manager, and that's really pretty awesome. If any of you have used Windows in the last 20 years and have ever tried to iconify your application when it's locked up, not so much. In X we haven't had that. But that really was a side effect of the fact that we wanted to have a common user interface for all the applications on the screen, and we didn't have shared libraries to make that easy to do. The other difference between X and Wayland is that X applications don't paint their own title bar, and they don't paint their own resize handles. So there's a bunch of these decorations around your window that aren't painted with your toolkit. So if you run a Qt application inside a GTK desktop, then the decorations around your Qt application are GTK decorations. So now your application has two looks and feel. It has the inside look and feel, which looks like Qt, and the border look and feel, which looks like GTK. So it's pretty awesome that there are two different look and feels. With Wayland, because there's no decorations in the window system server and there's no external window manager, there's no place to paint the decorations outside of the application. So that means the application gets to paint all of its own decorations. And I know it's a big burden for your toolkit to have to paint its own decorations, but fortunately GTK and Qt already know how to do this. So it's actually no additional work to you. And the fact that we have toolkits that can manage all this, the toolkits know exactly what they paint. And the toolkits have been trying to use window manager hints for 20 years, trying to get the window manager to paint what they want, instead of just painting what they want themselves. So internal window manager turns out to be a huge feature. Client-side window management turns out to be a huge feature for application presentation because you get a consistent look and feel across your whole application. Now people complain that now you're not going to have a consistent look and feel across your desktop. Yeah, that's because you didn't have a consistent look and feel across your desktop. You just had this notion that you had some parts of your desktop were consistent across applications and some parts weren't. So we have a different boundary of where the consistency is going to be. We think that having it be consistent across the whole application is probably more useful than having it be consistent between having the window manipulation decorations be consistent across applications. That was the funny thing. I started trying to write a list of what's different from an application perspective between X and Wayland. And that's really about all I came up with. It was really those three fundamental architectural differences. There's not a lot else that's different. Now the cool part is because We own the whole stack. We own the X piece, we own the Wayland piece, we own the kernel. We can change whatever we need to make it all work together. So one of the things we're working very hard to make sure we do is share all of our code. Oddly, we don't want to replicate any of the code. So one of the cool things about moving to Wayland is all of a sudden, because we've done work in the last, well, not all of a sudden, in the last 7 years, we spent a huge amount of time getting functionality that is fundamentally operating system functionality, moving it out of the X server. The X server used to have PCI remapping code. The X server used to have x86 BIOS emulation code. The X server used to have direct mode setting operations that manipulated device registers from user space. It still does in some cases. All of that has been pushed, for the most part, down into the kernel. So now the kernel provides actual device drivers for graphics devices. They can manage the output modes, they can do quick rendering, they can do memory management, they can do scheduling, all that kind of operating system stuff is actually in the operating system now. So because we've done that, all of a sudden, all those pieces are automatically shareable across all the Windows systems. Another piece that we worked really hard on is to make sure that the OpenGL implementations are shareable across Windows systems. The OpenGL, in particular, the DRI2 APIs that X created, makes it very easy for a new Windows system to just use the existing OpenGL libraries and talk to a new Windows system. So we have the EGL bindings in Mesa right now that Wayland is using, which means I can take exactly the same OpenGL library and run an application on Wayland or run an application on X. So the application doesn't see any difference in terms of its GL operations. It just sees differences in terms of its Windows system operations. So this huge burden of porting applications from X to a new Windows system is greatly reduced because all the rendering stuff is the same if you're using OpenGL or some other standard API. Your media APIs, VA API, VPAU, those are designed to be, well, VA API is designed to be Windows system agnostic. And so you can do media acceleration just like you can do GL acceleration on Wayland or on X. All the kernel driver stuff is of course shared with our mode setting stuff that's been moved into the kernel, so you get all of the Wayland mode setting stuff just works and gives you all the functionality of X. That was a huge barrier to former attempts to replace X. Because people would say, well, you have to replace all of the X mode setting code in all of your drivers before your drivers can do anything. But that was a huge barrier to entry. We removed that barrier by pushing all the mode setting stuff into the kernel, making it very easy to add a KMS backend for Wayland. So Wayland right now has an X backend that will run on top of your X server, or it has a KMS backend that will run native on the hardware. And that, those were weeks of coding that work on all hardware that supports the KMS APIs instead of years of coding to port every driver to a new Windows system. But of course, all the execution management so that your graphics acceleration stuff just works across all these different Windows systems. That's also in the kernel. So another interesting piece that we have here is we have the X2D acceleration code. There are some useful acceleration operations that you can do for Phoronix protocol. You can copy stuff around on the screen. You can paint stuff on the screen. Some fairly simple operations that are bulk memory operations that take a huge amount of CPU time and done in software, where it's really nice to be able to do those with the accelerator. And we have a bunch of 2D acceleration code in all the various drivers. Well, what are we going to do in the Wayland environment? Well, it turns out in the Wayland environment, we can just use it. All those acceleration operations are using these kernel execution management APIs. And so we have the ability to take that code and stick it and leave it on top of its kernel interfaces and just use it. So in the current X-Wayland environment running on top of Intel graphics, we've hacked up the 2D driver so that it does the pieces that are necessary by unhooking the mode setting code and just using the acceleration code to draw all the same 2D operations that we were doing in the native X server. So we have, because we have the ability to fix X and we have the ability to fix Wayland, now all of a sudden we can integrate X and Wayland very tightly together in terms of sharing the same kernel infrastructure. And now X can get all the same acceleration that it had on top of Wayland, the same that it used to have direct on the hardware. So X performance for rendering is the same between Wayland and non-Wayland. Kind of useful. So what are the performance implications for X? Right? One of the big problems we have with running X on another Windows system is typically the performance becomes abysmal. If you look at X running on Windows, for instance, all the drawing in that environment, all the 2D X drawing is done with software. All the X rendering operations are done with software. And that means that if you're doing, if you're trying to run a browser with a lot of scrolling, or any other application that has a lot of bulk memory operations, you see some significant lag. It becomes pretty jerky and pretty slow. And screen updates lag as the application takes all that software rendering and paints it into the fundamental window, the underlying Windows system, and does a bunch of memory copying, which we're desperate to avoid in all environments. Because we're able to fix the X drivers, and because Wayland is cooperating with this environment, with this endeavor, we can actually use the core X rendering stuff to provide into the kernel using our existing acceleration paths, and you get full-speed 2D rendering. The interesting part, of course, is that even things like indirect GLX. So your GLX paths go through all the existing accelerated GLX paths in the X server. Not that you should be using that, but it does work. Of course, direct rendering, totally unchanged. Direct rendering applications render directly to the kernel. Their images are sitting down there in the kernel and then get sucked across the Wayland Windows system when you do a screen update to the X server. Now for buffer swaps, that's the time when the application actually sends information from the X server to the West End compositor. When you want to actually update the contents on the screen, it happens once every frame, so every 16 milliseconds. It used to be in the days of the X compositing manager, the X server would set the damage events to the compositing manager, which would then gather all the damage events, figure out what had changed on the screen, and construct a new image with GL, paint it with GL, and then tell the X server to update the screen. So now you have the X server sending damage events to the compositing manager constructing a new image with GL, and then the compositing manager telling the X server, please update what's on the screen. So you have an extra context switch there. In Weston, the X server tells the Weston compositing Windows system that it has new contents of the applications. The Weston compositor then generates a new frame using OpenGL and doesn't tell anybody other than the kernel to update a new frame. So independent of whether running native Wayland applications is faster than running native X applications, one of the cool things about moving to X on top of Wayland is we're actually going to reduce the number of context switches required to display X applications. So the overall result may well be that X on top of Wayland is faster than native X. Probably not perceptible, again, because that context switch only happens once a frame. So nominally once every 16 milliseconds.
Let's just say power, right?
Yeah. Yeah, I'll say power. I'm going to be traversing less memory, so I'll be hitting fewer cache lines, so I don't have these replicated data structures. Yeah. Yeah, fewer context switches. So normally you talk about doing Windows system on Windows system, you talk about, well, how much performance am I going to lose? Well, at this point, we don't have any good numbers yet, but, the back of the envelope calculation says, well, it may actually be faster. Yeah, it's crazy. Why didn't we do this earlier? Okay, well, it's not all ponies and rainbows. Wayland is a very different Windows system for X, and there's a bunch of impedance mismatching that we have to take care of. Window management on top of X window management on top of a combined X Wayland environment means that we need to have an X window manager. X almost requires an external window manager. Now, it's funny that in the XWin, the X on Windows project and the X on OS X project, both of those stick this external window manager inside the X server as a separate thread that communicates with the X server through the X protocol. So yes, it's in the same address space, but it's an X application. It's an X client speaking X protocol. I've done this for a while. Trying to get a window manager running inside the X server without speaking X protocol turns out to be really inconvenient. It's much easier just to have the window manager speaking the X protocol. So in the Wayland world, the current plan, this is one thing that hasn't been implemented yet. The current plan is to have an external application which acts as an X window manager and proxies all of the window management that the X applications needs with the Western compositor. So you have this Wayland-specific X window manager. It translates between the ICM and the enhanced window management hints that the applications are doing and turns those into Wayland protocol. So the application says, here's my size hints, and the the Weston ex-Wayland window manager says, oh, those Hisense, yeah, let me resize you and put you over here like this, and communicates with Weston and tells it what's going on. Oh, here's my new title. It sends the new title off to Weston. And the other thing, of course, that this ex-Wayland window manager has to do is it has to provide decorations. So, of course, your X windows are going to have consistent decorations across all of them because they'll all be decorated with the ex-Wayland window manager, whereas your Wayland applications will all have whatever decorations they put on themselves. So here's an opportunity for more confusion on the desktop as you have your X application look and feel, your Wayland application look and feel, your Wayland decoration look and feel, and your X decoration look and feel. So they can all look different. It's an opportunity for distribution vendors to exercise their unifying thematic whatever they do. Yeah. It's a market opportunity. There's always a market opportunity there. Okay.
We can sell themes.
Oh, you can sell themes. And the more expensive themes is you could have an uplift for your X add-on package for your theme. Right? You've got your Wayland theme, and then you've got your X add-on package for the X theme version of that. Okay, so what do we have to do to the X server? I actually went, Christian recently rebased all of the X-Wayland changes on top of the X server 1.12 version, so it was really easy to go and see all of the changes in one list. There's like 50 patches to the X server to make X run on Wayland. That's it, just like 50 patches. I didn't count, but it's like, a page or less. So one of the things it obviously wants to do is automatically redirect top-level windows. That's so that all of your application content doesn't land inside the root window, but lands in per application window buffers. So now the compositing manager can take those per application buffers and pump those into Weston and display them on the screen. The other thing it has to do is it has to stop the X server from looking at all those USB EDDEV devices. Right? We don't want the X server directly communicating with your mouse or your keyboard, because the X server needs to get its input from Weston. And then what it does is that it provides these virtual X keyboard and mouse devices. So you note there's a big gap here. There's no touchscreen, touchpad devices. There's a bunch of stuff that needs to be done there. I'll talk about in a minute. Inside the X video driver, what do we need to do? Well, we need to stop doing mode setting. That's a big piece. Yeah, not doing stuff is pretty easy. We need to get the mode information from Wayland. So we actually have to talk with Wayland and see what the screen sizes it provides are, what modes are available, and dump those back into the render configuration. The current XF86 video Intel hacks for Wayland have a really ugly hack for window move and resize because there's no window manager yet. So if oh man, it brings me back. You hold the Alt key down and click left in the window, you can drag them around. And if you hold the Alt key down and click right, you can resize your window. Any of you used X10? Yeah, that's how X10 worked. That was awesome. The X10 window manager, there was no decorations, which was nice. It didn't take up any of your screen with those horrible window decorations. You did your whole screen for your Emacs content. Obviously, those ugly hacks, the goal there is to replace those with the X-Wayland window manager. The other thing it has to do is it's no longer in control of DRM. It's just another DRM client. It's just like an OpenGL application. It's just like a media player application. It's using DRM, and it's allocating DRM buffers in the context of the master owned by Wayland, and it paints content into those and hands those buffers to Wayland. There's no magic master in the X server anymore. That's all owned by the underlying KMS Wayland environment. So those are the only changes. That I think there are 8 or 9 patches in the 2D driver to make it work with Wayland. So we're talking a totally minor number of hacks to get stuff to work. Now, this is a great improvement over the number of hacks that are required to run X on top of Microsoft Windows. There we're talking about a whole project of 4 people that have been working for 5 years to try to get X working on Windows. And to get X working on Wayland, well, it was really pretty easy, because we aren't changing a bunch of fundamental stuff that X relies on. So in Wayland, window management is very different from the way X does window management. Obviously, we have client-side decorations. I have a great anecdote about that. It was February. We had a meeting just before FOSDEM. And I was doing a little presentation during it, and talking about client-side decorations. And I put up this client-side decorations you know, that Wayland requires client-side decorations, and Kristen Hochberg stood up and said, no, 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 Wayland does not provide decorations. Clients have to paint. And it took him about 5 minutes for us to calm him down before he realized that we were agreeing with him. Apparently he gets this a lot from people who are coming from the X environment, saying, why doesn't the Windows system provide the decorations? Well, the fundamental reason is really simple. You have a single buffer full of content, a single image buffer in the kernel full of your application content. If you want to be able to rotate that, if you want to be able to scale that, your window decorations have to be painted in the same buffer. If they're painted in another buffer and you try to paste them together, there will always be a seam between the decoration and the content. So you cannot put the decorations outside the content if you want it to scale and rotate nicely. So if you want it to look good, you have to paint the decorations in the application. Furthermore, you don't want to pollute the Wayland server with a bunch of GUI stuff. Right? You don't want the Wayland server having a bunch of linking in your entire GTK library just to paint decorations on your windows. Thirdly, you want the application responsible for its own window management so that when you click the buttons, you get the right look and feel of that application. And the application can respond appropriately so that when you're doing resizing, the application knows it's being resized and acts appropriately. The application has to resize itself. In the X world, when you resize an application, the window system tells the application, oh, your window is this new size, and I've just painted crap all over your screen, showing your application contents partially in the new size, partially in the old size. Enjoy. You know, in 1987, when you could resize windows, it was awesome. And the fact that the screen looked terrible as you were resizing didn't matter because systems were so slow. We resized by rubber banding with a little extra rubber band on your screen the new size, and then the application, it would resize once to the new size, and your application would be told. In 1989, I implemented opaque resize just as a hack in TWM at the time, and all my coworkers said, oh, that'll never work, it's way too slow. It's like, wow, on my 16 megahertz MIPS X station, this is almost plausible. 20 years later, it's actually, yeah, why would you do anything else? Of course, doing client-side decorations gives us that integrated look and feel for the whole application. We don't have this boundary between application and window management. And of course, the applications can integrate the decorations into their look and feel. So they're no longer, the decorations don't have to be a rectangular area at the top of the window and rectangular areas along the sides. We can have a credible area at the lower right corner to resize the windows. Anybody seen the horrible hacks in GNOME right now, where the GNOME application detects that you've clicked in the resize handle at the lower right-hand corner of your screen and forwards that to the window manager? Oh, hey, somebody clicked down here, you want to resize me now? Yeah, that's really disgusting. So the application now is responsible for figuring out, oh, somebody clicked the resize handle. I should resize my window. Now, there are some hacks in Wayland to improve the performance of some of these operations and make things a little simpler. For instance, when you want to move a window on the screen, just drag it around, not resize it. The Wayland server actually, you can actually tell the Wayland server, when they click up here, yeah, move my window and have it follow the mouse. That means you can move the windows around really fast and they're nice and snappy. So you know, obviously we can tweak the Wayland protocol to improve window management and add some additional hacks. But the fundamental operation of having the client initiate all the window management means that we can add stuff to accelerate that later, but we're never going to lose the ability for applications to manage their own windows, which means we can get whatever UI we want, we can make it look as nice as we want. And we're talking about hacks or stuck applications where you can move a window off the screen if you need to if it's stuck. You can just declare, you know, a little area on the top in your title bar. If somebody clicks in here, then, you know, minimize my application or to put it in the dock or whatever you want to do. So there are hacks like that we can do in the protocol to get around the fact that stuck applications can now impact the system. As I said, for the external window management in X, we need to have a Wayland-specific X window manager. Obviously, the Wayland window manager is going to be painting all the X decorations, and it has to deal with all the window management-specific ICM and EWMH stuff. Now, we read through all those documents recently again for the 50th time for some of us, and if you read through them today, it's like, wow, you know, all of this stuff to hack around brokenness in X. You know, you have to have times, you have to add a timestamp here because X forgot to put a timestamp in this event, and you have to have synchronization here and locking here because there's no event at this particular point in the X stream. So the nice part about rereading that with an eye to how we're going to implement that functionality on Wayland is that, oh, 99% of this document just doesn't apply because it's all for dealing with the asynchronous nature of X window management and specific bugs in the X protocol. So the things that are left are things like the title bar settings and the name of your window and you know, other minor things like that, where the window system actually wants to know. If you want to have a name for your application for each window on the screen, so that when you're zooming around with your little alt tab thing, you can put a name down there instead of just having a picture of the window. So there are uses for some of those hints. Yeah.
So do you have to re-implement all those hacks when you do your free slides previous layer for translating between the two?
Yeah, that's what this is, right? This is your window manager that's translating between the ICM stuff and Wayland. This is that external window manager.
But do you have to redo all those hacks because of do you have to re-implement the backends of the new window manager?
This window manager has to implement all of the ICM and EWMH hits. Yes.
Bugs?
Yes.
Okay.
I'm not fixing X.
Okay.
Yeah. But that stops here. Once you get to this window manager, then all of the X stuff is papered over, and this window manager can talk simple things to Wayland. Yeah. No, we're not going to fix X. Oh wait, yeah. We have fixed X in a lot of ways. There's a bunch of stuff in the Xfixes extension that you've gotten that have solved some of the persistent X problems. But we never really even considered fixing the stuff that's fixed by ICM because everybody's already got the ICM hacks in. Why would you go fix it better? You know, why would you fix it in a different way when the ICM stuff seems to work? And one of the horrible hacks in ICM, for instance, was color map management. There's this huge piece of the ICM spec for managing who gets to install color maps. When's the last time anybody here used 8-bit pseudo-color visual? Yeah, it's like 20 pages of the ICMs, all for dealing with pseudo-color visuals that nobody uses. Another big piece of our current desktop is cut, paste, and drag and drop. The X stuff was built before the notion of MIME and before the advent of Unicode. Yeah, think about that. How do you do text transfers in a non-Unicode world? Well, it turned out that there was this ISO standard number 2022, which is the multi-encoding transfer of text, where you actually stole a bit of encoding space from every possible encoding for shift-in and shift-out codes to shift encoding in the middle of your text byte stream. It was awesome. Yeah, well, we don't have to do that kind of stuff anymore, right? We have UTF-8 for text, which most people accept now. We have MIME labeling to tell us what kind of objects are. X had all of its own object labeling, right? What kind of object is this? Well, you know, I have this magic X add-on that tells me the type of object it is. Which meant that applications couldn't easily tell another application, oh, I have an open office document. Well, we now have the MIME stuff. So Wayland uses MIME. Another stuff that it does is it does direct client-to-client data transfer. And what the Wayland protocol does is it actually, one application provides a file descriptor to it. It's passing it to the Unix domain socket, and it passes that file descriptor to the other application. So now the applications have a file descriptor between the two, and the sync application can just suck on this file descriptor while the source application dumps data into it. So we aren't passing data through the X server. Again, another 10 pages of the ICM was all about how to do large bulk data transfer through the X server, which has a limited amount of storage for properties. And so, you know, we re-implemented TCP on top of X properties. So Wayland just says, you know, that was kind of an interesting hack. Some of us have done worse things on top of X than that, but we're not going to do that at all. You get a file descriptor and you pass it along and the data comes through the file descriptor. So how do we work with those in the Wayland environment? We're just going to obviously proxy them, right? It's really pretty simple to proxy a file descriptor into an X property. You just have some proxy, probably the X Wayland window manager, which will do the Wayland file descriptor and MIME stuff, and just translate those directly to the appropriate X requests. And we have a giant pile of code in the X Wayland window manager to do incremental data transfers with X. Not too complicated, fortunately. Another neat hack that Christian did the first time he started X was, how do you start the X server? Well, you could start it when the session started up, right? Make it part of your session in initialization. Oh yeah, I'd like to have an X server for this session. Obviously, that's going to introduce extra lag to startup, and you're sucking a bunch of memory that you may not use if you don't have X applications. We could require that applications that it be started manually, like a lot like Genome Terminal. When you run a console application, you can have a little checkbox in the icon in your menu that says, "Oh, this has to be run inside Genome Terminal." You can have a little checkbox in your application. "Oh, this has to have an X server to run." Right? You can imagine hacking up all your session management to do this. Instead, there's a really simple option. We have the Western compositor just listening on the X socket. When it starts up, it just opens up, temp X Unix -0 and listens on it. And if anybody connects to it, it says, "Sure, you can connect to X." Yeah, sure. And then it takes the file descriptor for the listen socket and the file descriptor for the connected socket and hands them to a newly created X process. It basically forks X. When X starts up, it connects back to Weston and sucks those two file descriptors over its pipe that it connects to Wayland. And now it uses that, sets up one as a listen server and starts talking X over the one that connected to. Yeah.
Why don't you use systemd for that? Because that's what that does.
Systemd, well, Leonard says that systemd can't start X.
Oh.
And one of the disadvantages of using systemd, of course, is that it's not run in the user's session. Do you have a per user system?
Yes.
Yeah. It would be nice if system. I would frankly rather systemd do this, but by having Weston started, it works today.
Is that only because of the user?
What?
Only because of the user session? Because
I don't know. Leonard said that the systemd really couldn't start X. It was like, no, I'm sorry, I can't do that. Okay.
Because the whole listening on socket.
I know. It's all the same. Yeah.
Systemds only have the ecosystem as well. There's the systemd is not being used on the Debian distributions.
Yeah.
When there's time, this gets.
Yeah. So in any case, obviously the same hack. Obviously, systemd. If systemd could support this, we could use systemd. But it's like 20 lines of code inside Weston to do this. It's totally true. So
that's what OS X does. With their startup thing, they watch this and they do that. And
Yeah, they do watch it.
Yeah.
Can you shut down the X server and just say, I've finished with that?
Oh, the X server has a mode when it runs out of clients, it turns on, it shuts down automatically.
And you can listening socket back to the Western.
Oh well, the Weston already has the listening socket, right? It hasn't gotten rid of it. Yeah, I don't. That part doesn't work yet, I don't think. But yeah, obviously that's a part of the puzzle here. So the X server will shut down when your last X application exits. That already happens automatically. It has exit on last closed magic flag. So that exists. Yeah. Now we just need to have Weston listen for the SIG file, reap it, and go back and listen to the X socket.
Again, what's systemd?
Yeah. So there are still a few remaining issues. Wayland input is in flux right now. We're trying to figure out what to do with keyboards. I have a lovely slide about that. And there's a bunch of questions about, not really questions, we just have a bunch of code to write to support touchscreens and touchpads. The X input 2.2 stuff that was released in the 1.12 X server has a huge amount of new support for touchpads, touchscreens, scroll wheels, and mice, all kinds of new cool stuff. That's useful at X. But it's also very useful as a research, as a way of saying how this should work. I think we did some pretty cool things with touchpads and touchscreens in particular, in terms of allowing for system global gestures and yet still allowing for reasonable responsiveness from applications. I don't know if you understand the problem here, but if you want to have a gesture where all 5 fingers on the screen does something magic system-wide, but regular touches should go through the applications, the problem with that is you have to have a timeout waiting to see if that first finger touch is going to be followed by 4 more. So in a system where you have global system-wide gestures processed before the application gets to see the underlying single touch, then you have to have a delay between when that single touch happens and when the application receives that single touch event. And in XI 2.2, what happens is we send that single touch event through to the application, and then we send later on, oh yes, you do actually get to commit the events, the actions that you've done with that single touch. Or no, the sequence of events you got starting with that first finger touch, those have been taken away from you, given to some application. So the intent is the application will provide all the UI feedback on the screen for that single touch, and then if you get all 5 fingers down, it will basically get canceled. So you have to have only cancelable operations with that single finger. That's some of the stuff we did in XI 2.2, which we're going to bring into the Wayland environment, so we figure out how to make this work. Another thing I wanted to talk about, I think I have time, 15 minutes left, is I wanted to talk a little about remote Wayland applications and what that means in this environment. It's very separate from X, but it's very tightly tied to the X community, which has had this capability for such a long time. So remote Wayland applications, from my perspective, they're not fundamentally different from a local Wayland application, right? What does a Wayland application do? It draws an image into a buffer and hands that buffer to the Wayland server. Right now, the way that buffer is handed to the Wayland server is you take the DRM buffer ID for that, and you pass it through the Wayland socket to the Wayland server, just the buffer handle, right? So then the Wayland server can go ask the kernel, oh, I need the bits from this buffer, number 47, and it can go get the bits out of the kernel. So the big pixels don't transfer the pipe, but logically, the image is sent through the pipe, just as a little handle, right? The difference between a local Wayland application and a remote application is therefore really minor. In a network, you don't have this shared memory between the client and the server. So we have to translate the image. Well, that's pretty easy. You know, we have a lot of nice network image transports. So we're going to create a little Wayland proxy. It takes an image from the local client, so it's going to look like a Wayland server. You're going to send the buffer ID to it, the DRM buffer ID to it. It's going to pick up that DRM buffer ID and then go map the buffer and send it over the network. It can do things like use the media engine to encode it and end tag it. It could do stuff like use it could use other hardware acceleration mechanisms to get the data from the graphics hardware into the network. So it can totally bypass the CPU if it wanted to. It can compress it. It doesn't even have to be lossless. We can use a lossy compression mechanism. Come just displaying it on the screen. It's just a one-way image transfer. And we can either hack up the Wayland server to listen for this magic new compressed image protocol, or we can create another proxy on the inside of the wire. This is just like we use with SSH today, right? When you SSH through to X remotely. Does anybody run X raw over the wire anymore? Your wire's unsecure. Of course you don't run X over the wire because you're typing your visa numbers in it all the time. Yeah. So it can talk directly to the Wayland server, or it can talk through another proxy. So what's that going to do for performance? Well, one of the cool things is we can accelerate the rendering of that image with the GPU that's local to that application, right? Remember that X server that I talked about? It's just a local application that's not a DRM master, but it's talking to the local GPU doing acceleration. Well, these remote Wayland applications could use their local GPU and construct their images with a local GPU. One of the nice advantages of using Wayland instead of X is that Wayland has almost no round trips. So one of the huge performance-killing demons in X over the network right now is network latency. Turns out that X does not use any network bandwidth at all unless you're pushing images. And the only reason it uses network bandwidth in pushing images is because there's no compression at all. So if you eliminate the round trips by switching to the Wayland protocol, and you reduce the image size by using image compression, then you're actually going to get better remote application performance with Wayland than you do with X today. Obviously, there's a lot more questions to answer here in terms of actually doing the implementation of making it work and integrating with media compression engines and blah, blah, blah. But you know, my hand-waving argument says that this is actually going to be plausible and pretty usable. Wayland keyboard support is in flux right now. I wanted to talk about that because it's very relevant in the X world. Right now, Wayland keyboard support looks a lot like X. And in fact, Wayland applications will be able to use libxkv common to do the X key sim, X key code key sim to Unicode translations. Unfortunately, in the Wayland environment, this makes input methods really hard. I mean, in X, you have the ability to applicate multiple applications drawing in the same window. In Wayland, you can't do that. So when we talk about things like over-the-spot and on-the-spot editing, Wayland's going to make that very difficult. Right now, if you've ever looked inside the valves of XLib, XLib actually has a custom communication protocol for talking between XLib and your input method. So if you have an input method or one of those other Asian language input methods, there's a custom XLib protocol. GTK uses the same protocol for its input method translations. So you have all this huge application infrastructure to do text input. Does any other Windows system on the planet use this complicated mechanism? No. They all integrate the keystroke to text transformations in the Windows system itself. And so one of the simple ideas we had was that we would just go look at other Windows systems and see how they did keyboard handling and steal what looked good, because we knew X wasn't what we wanted. So that will make input methods integrated into the Windows system, make it all pretty. What does this mean for X Wayland? That's the big question. Because if we are no longer totally compatible with X, then we need to figure out how to make keyboards in X Wayland work like they do today. So what works today? The X Wayland X server backend works pretty well. It redirects Windows. The X server is automatically launched when you talk to it. We have a synthetic mouse and keyboard, so you can do input. We have no window manager. There's not so much for that, but we do have the ability to run X applications. The video Intel stuff all works. We bypass the KMS stuff, and we have direct running acceleration for all your 2D stuff. So your X applications run at full speed. What still needs doing? We still need to write this giant external X Wayland window manager. And we need to implement all the translations between drag and drop and cut and paste. And then we need to go through the long exercise of figuring out how to do more advanced input support in X Wayland. So that's the end of my presentation. If there are any questions, we have about 5 minutes or so. Yeah.
Will you be adding support for multimedia stuff? So taking video stream and displaying it?
Well, I talked about using VDPAU, which is our multimedia API here. So an application today that uses the API to do multimedia. In the Wayland environment, it gets to use the same API.
And could you also say, here's a sound file, play that on?
We don't do sound. This is a Windows system, does graphics. If you want to do sound, go talk to Pulsar.
For the multiple screen support, do you have a chance to get rid from the XR model, which basically is this giant virtual desktop?
Yes, Wayland doesn't. The Wayland model doesn't have a giant virtual desktop. It has multiple separate outputs. We did the giant virtual output in X because you can't move windows between screens in X. So in order to support the ability for moving windows between monitors in the X environment, they have to be the same screen. Most of the desktops now make that pretty transparent. You don't know that they're separate, that they're the same screen. They really do provide this notion of different monitors pretty nicely. So the fact that in X it's this nominally virtual desktop, it really isn't exposed to applications. In the Wayland environment, they really are totally separate.
So I'm going to explore it a little bit further. Since now you create actually individual desktop and stitch them together, can multiple seat having one Wayland session on each?
Well, you can have multiple seat with X today.
Okay.
There's no different with Wayland. I mean, Wayland provides a DRM device per hardware instantiation in the hardware, right? So you can have different Wayland servers talking to different DRM devices. That works in X today.
Okay. Usually the output part is easier to control. It's the input device.
Yeah. And people have hacks to figure out how to pick which devices go to which X server with input. But because USB doesn't have persistent naming and USB input devices don't have serial numbers, it's impossible to label them in a sensible way. So you end up with hacks trying to figure out what the bus topology is like in your environment and labeling specific hubs as belonging to specific users and using the USB bus topology to figure out who owns which input device. We don't have anything good and consistent there, though. That's just a bug in USB. But that works in X today and can work in Wayland as well. Question?
Yeah, so kind of in the related direction, does Wayland do anything for multiple GPUs, one frame buffers, and hybrid graphics?
With that stuff right now, we have a kernel support in the new DRM Prime interfaces. And in terms of integrating that into Wayland, the support for that, it will work very similar to the way that it works in X today. It's a fairly straightforward notion where you have the application rendering with the high-speed GPU and then having the data copied into the low-speed GPU's frame buffer. So that the prime mechanism, that's really a fairly straightforward kernel mechanism, and it's much more involved in buffer sharing and getting the image format between the two GPUs to be aligned, so that one GPU can write into a frame buffer that can be displayed by another GPU. So we have that working between Radeon and Intel today in a couple of sample laptops, and it seems to work pretty well. In terms of integrating that into Wayland, it's a simple matter of code. Yeah.
I guess you don't have anything to demo yet.
So it does work, but I don't have a demo working today. Yeah. Other questions or comments? Hey, thanks for coming up to the 25th floor. Enjoy the view for a few minutes and head down to your next session.